All right, welcome everybody. It's my pleasure to welcome Ariadna, who's visiting us virtually this week. Ariadna is an absolute expert in neutron star mergers and the post-merger evolution, and as you can maybe see from her background, especially in connection with short gamma ray bursts, which is also the topic of today's talk. Ariadna got her PhD at the University of Santa Cruz, working with Enrico Ramirez-Ruiz, and then recently moved to Northwestern as a Hubble Fellow, from where she is joining us now. And without further ado, I'll just hand it over to Ariadna.
Thank you very much, and thank you for the introduction. So I hope, let me just share my screen so that you can all see my presentation. Okay, you can see everything, right? Yes, okay. Yeah. It's pretty cool that we have the screen so that I can see what you see, so that it's like great. So thank you again for the introduction. So today I'll be talking about GW170817, everyone's favorite gamma ray burst in general, and what the jet can tell us about, well, the binary neutron star itself. So let me just begin by reminding you what happened. So as you probably all have heard, in 2017, LIGO found the first binary neutron star that was associated with an electromagnetic counterpart. So let me tell you like briefly what happened. So first, you have two neutron stars that are orbiting around each other. They are going to get closer and closer as they radiate gravitational waves. They carry energy and angular momentum. So as they get closer, tidal interactions are going to happen, and matter is going to become dynamically unstable. Well, it's also going to merge. And before the merger, you will have this spiral tails of unbound debris because mass is going to be ejected at the outer Lagrangian points. Now, after the merger, this is going to result in a hot, rapidly rotating hypermassive neutron star surrounded by an accretion disk. Now, depending on the mass, this hypermassive neutron star might or might not collapse into a black hole immediately. So in the case of GW170817, as we will argue, the remnant is believed to have been from a delayed collapse to a black hole. So again, after the binary mergers, we have first two options of the resulting object, depending on the mass of the merger. If the mass of the merger is larger than the mass at which self-gravitating objects collapse, then it will just promptly collapse into a black hole. If not, it'll remain as a hypermassive neutron star that is also differentially rotating and again hot and very rapidly rotating. In the case in particular, again, of GW170817, we know that this should have been a hypermassive neutron star just due to some mass arguments. Now, this is differentially rotating, but it's going to go into uniform rotation. So then we have two different threshold masses. So if this threshold mass, if the mass of the merger is less than this threshold mass, again, everything is more, than the threshold mass, everything is just going to collapse to a black hole again, but after a certain time. That we'll see later what I'm referring to as a time. If not, then it can remain as a stable magnetar. Now, in both of these scenarios, we expect the merger to have an accretion disk, and different mechanisms are going to occur that drive this relativistic jet. Now, due to some energetic arguments, we have reason to believe that GW170817 is the result of a delayed collapse to a black hole, which is pretty interesting. So now this is what happened with 170817. So now let me discuss all about the emission. So we know that in the case of GW170817, we're going to be left with an accretion disk surrounding a black hole. Now, due to magnetic stresses, material from the disk is going to be accreted onto the black hole, and it's going to launch a relativistic jet. Here I'm just showing some GRMHD simulations that show us that we should see this initially very powerful, very relativistic collimated jet. Now, in normal gamma ray burst, it is expected that this jet will emit in gamma rays, but for now, and that'll be called the prompt emission. But for the rest of the talk, I'm going to just talk about the afterglow and all the other kinds of emission. Now, from GW170817, we know that we should have observed a normal gamma ray burst. But this event was actually extremely rare because of all the uncharacteristic energy and scales compared to a normal gamma ray burst. So here I'm just briefly showing the initial energies and the time in which these energies, the T90, which is just where 90% of that energy is released, and the energy bands. Now, I know that not a lot of you do gamma rays, so I'll just say that in general, for a gamma ray burst, this energy should have been around 10 to the 51, or 10 to the 52. And another thing is that the X-ray just raised after way too many days. So this was extremely unusual and very rare for a normal gamma ray burst. So in this talk, I'll explain what we think we saw and how we can constrain some interesting properties using that information. I'll briefly talk about the thermal emission. So this is the thermal emission because, first of all, it's a very important emission because it was the discovery that led to all the other electromagnetic counterparts. So I won't go into a lot of detail, but again, finding the optical counterpart, which is the thermal emission, allowed us for localization and basically allowed us to study this amazing object. So 9 hours after LIGO sent the alert, the optical counterpart was found, and basically every telescope on Earth was pointed at that object, and it allowed us to find everything, X-ray, radio, you name it, which was really cool. And again, this thermal emission is unlike anything we've ever seen. So at first it was extremely, extremely blue, and after just a couple of days, it became very, very red. This is highly uncharacteristic and we have never seen that before because we had never seen this thermal kilonova emission. So how do we explain this kilonova or this thermal emission? So there are going to be several outflows, both during the merger, after the merger, and before the merger, that are going to be extremely dense with really high temperatures. And we're going to create what are called the R process elements, so elements such as gold, platinum. In particular, we are also going to create several lanthanides. There's a debate as to where, but in general, we know that we should have created lanthanides. And in general, and we will have this emission. So this material is going to expand, it's going to cool, and after some time, it's going to radioactively decay, and we will see that emission. So this is the kilonova emission. We will have two different components. So there's going to be a lanthanide free component, so it has lower opacity. And we're also going to have a slower moving material with, sorry, a faster moving material, slower moving material that's going to have lanthanides, which means very high opacity. So this material that is moving slower and it has high opacity, we're going to call the red component because it's going to peak later and it's also going to be redder. Whereas this blue component is going to be lanthanide free and it's going to be faster. There has been a lot of debate as to where these two components come from. In general, there's an understanding that at least the pre-merger material should have created some lanthanides, and most likely the post-merger material should have created some lanthanide-free ejecta, but there's still a debate there that I'm not going to go into a lot of detail. What's really nice about this discovery is that it was a very cool thing that theory found all of this before the actual observation. And after we observed this, both the blue kilonova and the red kilonova, people have already had models for this. So here I'm just showing a movie of the brightness as a function of time. These dots are the real data, whereas these are just the models that had been going around from before. So it's pretty cool because this was a win for theory because theory predicted all of this before the actual observation. So we could explain that, and everyone was really, really happy about this. And we could predict how many mass was ejected and a lot about the opacities. So everyone was happy. But the non-thermal emission was still a mystery. So the non-thermal emission, again, is particularly very rare and very interesting. So here I'm just plotting the X-rays and radio from this event. And again, this is very highly uncharacteristic of a gamma ray burst. And I'll show you what a normal afterglow from a gamma ray burst looks like. So the non-thermal emission comes from synchrotron emission from when the jet is interacting with the ambient medium, or when some kind of ejecta is interacting with the ambient medium, and you get synchrotron emission. In general, this is what a gamma ray burst afterglow, or like the non-thermal emission, should look like. So we're going to have this relativistic jet that is going to be composed of relativistically moving electrons. These electrons are going to be beamed just due to some relativistic effects. So we're actually not going to be able to see the entire cone because the electrons are going to be, we are only going to be able to see electrons at an angle that's lower than 1 over the Lorentz factor of the jet. So this is what, again, the normal afterglow curve looks like. If we would be observing the gamma ray burst from like on axis, so we would need to be observing the gamma ray burst jet. Now, what happens if we're actually not looking at it on axis? We're actually looking at it a little bit off axis, for example. So, yeah. So in that case, we would be able to see much, much less electrons. We wouldn't be able to see all the electrons. We would only be able to see a fraction. So the flux would be highly diminished. So we would be able to see like this curve here. But as material is going to traverse through the wind, it's going to get accelerated, which means that the Lorentz factor decreases, which means that the opening angle of the electrons increases. Therefore, we're going to be able to see more and more of the electrons that are radiating the synchrotron radiation. So we get to see more and more flux. At some point, when the opening angle of the electrons is equal to the observed angle, we'll be able to see everything, and we're able to recover the usual afterglow from the gamma rays. So this curve that I showed you is what a normal off-axis gamma ray burst afterglow should look like. And as you can see, it resembles the non-thermal component of this GW170817. So this off-axis gamma ray burst is one of the ways in which we could explain the afterglow. There is another interesting way, but I'm going to focus more on this off-axis. So then we can say that the non-thermal component, it's just a normal gamma ray burst, but seen off-axis. I mean, it's one of the explanations. But there is still a problem. So if we just assume that the relativistic jet is just a normal top hat jet, which is just a regular cone that's seen off-axis, that alone cannot explain the emission. What we actually need is that the jet has large amount of energy at larger angles. So this is required by early afterglow observations. So the question arises, how can we produce this large energy at larger angles, or how can we give the jet structure? That is another way to see it. So one way is to have it interact with outflows, and this is where my work comes in. So here what I'm showing is that some simulations of a jet interacting with some ambient medium. This is the density, and this is the Lorentz factor of the jet. This was initially a top hat jet, but eventually, as it interacts with the ambient medium, it's going to be collimated and it's going to be shaped by the ambient medium. So instead of seeing just a regular like collimated jet, we actually see this kind of wing-like structure, which is just larger energy. It's just large energy at larger angles, which is pretty cool. So when the jet encounters with the wind, the head of the jet is going to be decelerated. And if we balance the ramp pressure of the jet and the ambient medium, we can actually obtain the velocity of the head of the jet. I'm sorry that I'm putting a lot of equations. You don't have to think about them a lot. I just wanted to say that the velocity of the head of the jet is highly dependent on, first of all, the density of the jet, which is related to the luminosity of the jet, and the density of the ambient medium. This is, of course, not surprising, because if we have a jet that's interacting with the medium, they will eventually interact. Another thing that's going to happen is that as the jet interacts with the medium, excess energy is going to be accumulated in what we call the cocoon, which is an extremely important thing that can actually also emit its own afterglow, and it could also emit even gamma rays. So if we want a visible gamma ray burst, we need to have that the head of the jet needs to break free from the wind and emerge out relativistically. So if we have some kind of ambient medium that's blocking the jet, we need the jet to actually be able to plow through it, or else it can get choked and we wouldn't be able to see anything. Now, as the jet traverses through the medium, what's also going to happen is that this cocoon that I talked about is going to exert pressure in the jet. It's going to exert pressure laterally. Depending on how much pressure this cocoon exerts on the jet can actually be collimated, or it can remain uncollimated. If the cocoon is actually very powerful, it will collimate the jet, and the jet will just be like a cylinder. Another really nice thing about this off-axis event is that we can also explain the prompt gamma ray bursts. So what we think is that the gamma ray bursts, the gamma rays from the gamma ray bursts comes from when the cocoon is breaking out from this medium. So just in a little bit off axis, which is really, really nice. So this is like the cocoon breakout. This is a model that's done by Orr, which I think is giving a talk later. So keep an eye on that. And it's really nice because then we can self-consistently explain everything. And also the cocoon itself can explain all the other emission, which is really nice. So now let's do a lot of different things. So I've been talking all about the ambient medium and how the jet interacts with the ambient medium, but I haven't actually explained what is the ambient medium. What will the jet interact with? So let me tell you about some different outflows that are going to naturally occur in this environment. So first of all, I talked a little bit about what we call the dynamical ejecta, which is when before the merger, we have these neutron stars that have the spiral tail. So that is one thing that could interact with the jet. In particular, I'm going to focus on things that happen in the post-merger phase. So after we have the merger, let me remind everyone that we have this hot hypermassive neutron star that's going to live for several milliseconds. I'm going to later say how many. It's going to live for several milliseconds. Not surprisingly, the material surrounding the binary neutron star is going to be extremely neutron rich. And since, again, it's very hot, it's also very dense. This is the perfect place for the beta process to occur, and we're going to have lots and lots of neutrinos. These neutrinos are going to interact with the matter surrounding them, and they're going to drive this baryon-loaded wind. Even though the neutrinos barely interact with the matter, we have so many neutrinos that there's going to be a very powerful wind, actually, made from baryons, but from the interaction of neutrinos. So this is known as a neutrino-driven wind. Now, this wind in particular, it typically lasts for the duration of the hypermassive neutron star. So the duration of this wind, and I'll be very I'll be very emphatic because this is a very important point. The duration of this wind is dependent on the lifetime of the hot hypermassive neutron star. Now, why do we care about that? So the neutron star equation of state, as you probably, a lot of you know, tells you, well, about the mass radius relation, but it also tells you what is the lifetime of this hot hypermassive neutron star. It tells you what the maximum mass is. And if we can constrain the delay time between the lifetime of the hot hypermassive neutron star, which means the delay time between the merger and the collapse to a black hole, if we can constrain this time, we'll be able to say a lot about the equation of state of neutron stars, which is an incredibly important information to have, and it's Nobel worthy. So constraining this delay time is a top priority in this field. And again, this neutrino-driven wind tells you a lot about the lifetime of the hot hypermassive neutron star, because after it collapses to a black hole, you won't have as many neutrinos, and the wind is not going to be as powerful. There have been a lot of different simulations surrounding this neutrino-driven wind. So in particular, for my simulations, we took results from global simulations from this paper by Albino Perego et al., where they use some spectral scheme for some spectral leakage scheme for neutrinos that takes into consideration matter reabsorption, and they just do the simulation. So we took that wind. And additionally, there's also, I mentioned a little bit, but there's also another type of outflow. So when you have the accretion disk and the black hole, this is again after the merger itself, after the hot hypermassive neutron star collapses, you have the black hole and the accretion disk. There's going to be magnetic stresses that drive material from the accretion disk onto the black hole. And not only will a very powerful relativistic jet will be launched, but also you will have this disk outflow that's going to occur. So I'm going to call that the magnetized wind. And we also have simulations for this. So for the purpose of this work, I took the information from simulations by Agnieszka Janiuk. This is our results from 2D general relativistic magnetohydrodynamical simulations that consider the effects of neutrino cooling analytically. So now that we have these two different winds, and now that we have the density profile of these two different winds, let's see what we can do with that. So what I did was I used Mezcal, which is a special relativity hydrodynamical code developed by a guy in Mexico in the Institute of Nuclear Sciences. So what we did first is let's launch a wind. So for example, a neutrino-driven wind from global simulations. We also use a spherical wind or a magnetized wind. So we put a wind first. After a certain delay time that I'm going to call TW, or time of the wind, the jet is launched. Now, I'll be also emphatic here. This delay time that I'm going to call TW, in the case of the neutrino-driven wind, is the lifetime of the hypermassive neutron star. So this is the duration of the wind. And again, it is related to the hypermassive neutron star if we're talking about the neutrino-driven wind. Now that the jet is launched, the jet is a top hat jet, and it lasts for a time T jet. And then we just let the simulation run and see the results. So here what I'm showing is the different winds that we took from those different simulations as a function of angle. So this is just a normal spherical wind. This is the neutrino-driven wind, and here is just a magnetized wind. Now this basically will be our initial conditions for the wind. What I want you to notice is that, not surprisingly, these two winds are very much alike. So in the polar region, the density is much, much lower. And as we go into the equatorial regions, the density increases. This is not surprising because both of these winds come from the disk itself. So we kind of expected these winds to have a profile that comes like from the disk. So now let me show you what the simulation looks like. So here I'll be showing a movie. You can actually, you may be able to see the wind right here if you squint your eyes. This is the density and this is the Lorentz factor. So this white bar just represents a distance of 1.5 c. And what I want you to notice most of all is that first the jet is going to be top hat. So it's going to be like this conical structure. And then it's going to be shaped by the wind. So it's actually going to lose its initial top hat feature. So instead of just being like a cone, it's going to have this wing-like structure, and it's going to have large energy at larger angles. So let me just go a little bit into the physics of what's going to happen. Here, what I'm showing are 3 different pictures of 3 different times. This is all for a spherical wind, but it's the same idea for a neutrino-driven wind. Again, this line right here represents the scale. The white lines represent Lorentz factor contour plots, and this is just the density. So initially, what's going to happen is that the velocity of the head of the jet is just going to be defined. It's just going to be decided with this L tilde that we talked about before. It's going to be related to density of the jet, or the luminosity of the jet, and the density of the wind. If the wind is more dense, then the velocity of the head of the jet decreases. If the jet is more powerful, it increases, not surprising. So this I'm going to just call the initial part. But as the jet plows through the wind, we get to see that the cocoon is formed. And we actually get to see the first stages of the cocoon right here. Energy is starting to get accumulated. And at some point, the cocoon is going to be very powerful, and it's going to collimate the jet. Now, what happens is that you get this recollimation shock. This decreases the jet's cross section, and it enters again the collimation regime. Now, the velocity of the head of the jet depends mainly on the structure of the wind and the cocoon's pressure. So we can actually see it right here that the jet is now collimated. Here's the cocoon, and we'll see that the velocity changes. Now, if the jet gets out of the wind, then there is a steep decline in density, and the jet is accelerated to very high Lorentz factors. What I'm showing right here is just the position of the head of the jet as a function of time. And this is for the 3 different stages that I'm talking about. So this blue line right here represents the initial regime, where the velocity is just like 0.4 c. This right here is the collimated regime, where the velocity increases because we just have a decrease in the jet's cross section. And after it breaks from the wind, which is represented by this line, we actually see this really acceleration in the jet. So the purple line represents the results from the simulations, and the dashed line represents our analytical estimates. So it's really interesting that we can say what happens to the jet depending on exactly where it changes, when the cocoon is formed, and we can say a lot about the dynamics of the jet. Another thing that
Can I ask one quick question?
Sure.
How much does it depend on spatial density variations in the wind? Better say if I launch the wind from a mass flux, if that changes in time, or does that get
with
imprinted?
time? Yeah.
If you initially have a very high dense wind and then you have a lower dense wind, would that change the outcome of that?
So in our case in particular, for example, this actually does change the density. So the density here should be a little bit larger. It changes with time once the jet is launched. These analytical estimates you could take into account as a function of time. Like this cocoon's pressure. This cocoon's pressure, you can see from Elmer Bromberg's paper. it depends also on a lot of jet quantities. So if you had an m dot that change, so say a Wiens density that changes as a function of time, you could take that into account and you could put that as a function of time. That's pretty, you can do that. And you can also put that here. I mean, so I haven't done the simulations, but I'm almost confident that this should still happen. I mean, at least if the cocoon forms, it's going to enter the collimated regime for sure. And you could just change, you could just do this as a function of time, if that makes sense, like this analytical estimate.
Thank you.
Yeah, but good question. So another thing that we can say is that as the jet interacts with the wind, three different things can happen. So far I've just shown what I'm going to call successful jets, which as the word says, they are jets that break from the wind. So it could be that the jet is very powerful or that the wind is not that dense. But in general, if that happens, we'll see it as a successful jet. So I'm showing this here. Of course, if the wind is very, very powerful or the jet is very, very mild, then it could be the case that the jet never makes it out of the wind. And this is, I'm going to call a choked jet. There are also cases in between where it's marginally successful, like almost a tiny, tiny blip gets to leave the jet, the wind. Of course, we want a successful gamma ray burst if we want to see it. But in any case, all of these cases are interesting because choked jets are also expected, and these choked jets could also have their own signature because you could also have the cocoon and you could also have all these kinds of different things. Although in general, like this is the typical picture of a gamma ray burst. Now let me address, this is a very similar question. It's not as was asked. So what happens if we change the wind's profile? So this is, the simulations that I showed you was with the spherical wind, but I've been talking about a neutrino-driven wind and also magnetized wind. So what happens if we put those types of wind? This is, again, not as a function of time per se, but as a function of angle, what happens? So in the neutrino-driven wind, which here I'm just calling NDW, there is more density at higher angles. So the cocoon pressure is actually greater in this neutrino-driven wind case. So this makes the recollimation regime occur earlier, and thus the jet is actually going to come out faster. But there's not that big of a difference, mainly because if you recall this density profiles, the jet is going to be like, say, around less than 10 degrees, something like that. So if that happens, it's the density profiles are almost the same. So the big differences only occur at large angles, and we don't expect a very large jet. So in general, it doesn't make that big of a difference, but the jet should come out faster and it should come out earlier, also in the case of a neutrino-driven wind. Now, another thing that I want to say that we can say from the simulations is what happens if the duration of the jet or the duration of the wind are different. And here I'm going to just say that again, remind everyone that TW is intimately related to the lifetime of the hypermassive neutron star if we're talking about a neutrino-driven wind. So one question that we can ask is, okay, let's say that the jet lasts for more or the wind lasts for more, like what can we say about the outcome of the jet, and more importantly about the structure of the jet? So what we did was we did several simulations with different durations of the jet and durations of the wind, and here's what we learned. So not surprisingly, again, and this is all very intuitive, if the jet is interacting with the wind, it's going to get a structure. So if the jet interacts more time with the wind, it's going to get more structure. So it's going to get larger energy at larger angles. Again, this is all very intuitive, and the simulations just prove that it's not surprising, but it's just nice to see that our intuition is correct. So how can we show that? Let's focus on, for example, the same time of the jet, but different wind times. So for example, this yellow line and this like purple line. So they have the same duration of the jet, but they have different winds. So what happens is that this purple line, and here I'm just showing the energy as a function of angle. In this case, the one corresponds to the core angle, to the core angle, sorry. And the rest is the wind structure. So if we have the same jets, the jet duration and a different duration of the wind, not surprisingly, we're going to get larger energy at larger angles. So in here, as you see, the purple line has more energy at larger angles. And again, this just comes from intuition. If more time passes when the jet is interacting with the wind, then you get more structure. Now, whether a gamma ray burst is successful or not depends on whether the engine is still active when the jet breaks from the wind. So I mean, so far I've showed you all these three cases. So let's try to be more analytical. So when the jet reaches the edge of the wind, we're going to ask that it's relativistic and say that we need the engine to still be active by that point. And if we do that, then we consider a jet to be successful. So this condition can be written like this, where this is just the velocity in units of c. And in this plot, what I'm showing is just the luminosity needed for a jet to be successful as a function of the duration of the jet divided by the duration of the wind divided by the duration of the jet. So the dashed line represents this condition right here. And these are all the simulations. So this is for different winds, let's say well, no, this is for the same m dot, but different jet durations. So in here we have that if it's below this line, it should be unsuccessful. This one, I mean, it is successful, but it's like right in the line, so that's fine. But this is one of the conditions that we can say for a successful gamma ray burst, and I'm going to say another one. Now, all of this is to say that we can say when a gamma ray burst is successful or not, and this is important because we want to be able to observe it, so we need a successful gamma ray burst. So if we can constrain all these different quantities, we may be able to constrain this to wind, and if we do so, then we might be able to say something about the hypermassive neutron star, and in particular, the lifetime of the hypermassive neutron star, and in particular, we can constrain the lifetime of the hypermassive neutron star in GW170817. So before I go into doing that, which is the main purpose of this paper, let me just ask a different question, and this is work by Gerardo Urrutia. What about if the initial jet structure is not a top hat jet? So another interesting thing to do is check how the structure changes depending on the initial structure of the jet. So here I'm showing the results after 10 seconds of this is just the energy distribution as a function of angle. For very similar simulations, the main difference is that we changed the initial condition of the jet. So instead of it being a top hat, we began, for example, with a Gaussian type of jet or with a power law type of jet. And these different lines just represent different luminosities and different things. So ignore all of that and let's just focus on the three different dashed lines. So this one, it's this one and this one. Oh, sorry. Yeah, this one and this one, and the red one is here. So the red one is here. And what I want you to take away from this plot, which might be a little bit too much because I haven't talked a lot about this paper, is that, again, this is not surprising. It's all very intuitive. A jet with an initial structure is going to cause more structure. But the initial structure of the jet is not going to be preserved. If you start with a Gaussian jet, you're not going to end up with a Gaussian jet. And Gaussian jets are less energetic are larger angles than a power law, but more energetics at intermediate angles. So we can use this information if we have more and more, if we have more and more structure of the jets, like observations for the jet structure, we could try to see what kind of jet the central engine formed initially. Now let's relate all of this to GW170817, as I've been saying, because of course this is the biggest event that we have. And now that we have the simulations that can simulate different luminosities of the jet, different winds, and we can get the energy as a function of angle, we can say something about the lifetime of the hypermassive neutron star in GW170817. So several groups have used different energy profiles to obtain light curves that are consistent with this non-thermal emission. So here in the dashed lines, and this again is the energy as a function of angle. In the dashed lines, I'm just showing these energy profiles taken from all these different groups. So all of those can explain the observations of GW170817. One of the things that you can see right away is that all these different profiles need very large energy at large angles. so more than others, but in general, a top hat, you cannot just use a top hat jet, you need a structured jet. And overplotted are results from our simulations. So what I want you to notice is that, first of all, we can reproduce all these different energy profiles from our simulations, meaning that you can create all those profiles just by having the jet interact with several different winds, which is really nice. So you can naturally explain the jet structure by having it interact with winds that should definitely be there during the merger. So that's one thing that we can take from this plot. Another thing, let's go even further and let's try to put another constraint on the duration of the wind. So we can measure how much energy is needed at larger angles to reproduce observations and compare it with the results from the simulations. So here I'm plotting the energy inside the core angle divided by the energy outside the core angle. So you can think of this ratio right here as the energy. So if the ratio is less than 1, we have that the jet is the core of the jet is very powerful. It's a very jetted jet. Whereas if this number is low, then we have that the wings have large energy, so it's a more structured wind. So this is very jetted. This is very the wings have lots of structure. And this is just TW divided by Tjet. So this is the duration of the wind divided by the duration of the jet. And again, all these dashed lines represent the same energy profiles. And these are the results from our simulations. So what we can say about this plot is that we cannot have a very low duration of the jet duration of the wind divided by duration of the jet. Of the wind divided by the duration of the jet, yes. Because if that is the case, we will have that the jet is very powerful and we wouldn't be able to reproduce observations. So let's say approximately that we need the TW divided by Tjet to be around here. So everything that's below is we can just say that it should not happen because we wouldn't be able to reproduce the observations. So then we have two different constraints. So one constraint I already told you that we need the jet to remain active as it breaks from the wind. And we can also put a constraint that we should be in this area right here. So these two constraints together sets a constraint on TW or the lifetime of the hypermassive neutron star, or you could also think about the time of collapse. So the delay time between the merger itself and the collapse to a black hole. So if we combine all those different results, we get that the time of collapse should be around here. So it should have been like around a second, let's say, which is really nice because it's consistent with a lot of the literature. So a lot of different people have said that in the case of GW170817, it should have collapsed at around a second or something. So the hypermassive neutron star should have lasted about a second, which is really, really interesting. Now then the conclusions for this part is that GW170817 showed the need for a structured jet. This can be done by the interaction of the jet with the surrounding medium, which is going to shape the jet and could potentially choke it. Now we can also use numerical simulations to constrain binary parameters, such as this delay time right here. And we got a delay time that's consistent with the literature of around a second. And if I have time, I want to talk a little bit about some other work that I've been doing at Northwestern. I think I do, right?
Yes.
Okay, so this, which is very related to this, but it's a different type of thing. So all of the other work that I did was 2D simulations, hydrodynamical, and we put the jet by hand. So one of the things that I've been doing here at Northwestern, this is with really, really cool mentees. And again, this is work also by Or Gottlieb and some really nice mentees that I have here, is what we do is we put the black hole, we put a torus around the black hole, and we put some analytical prescription on the ejecta. So we use Hammer, which is a GPU accelerated general relativistic magnetohydrodynamical code. This is again 3D simulations. So everything is really nice. And we just let it evolve. what's cool about this project is that the torus itself, I mean, so we put a torus, which means that we do not put a jet by hand. The jet should be formed very self-consistently, and then it's going to interact with the ejecta. And we can, of course, change the density profile of the ejecta and magnetic field of the torus. In this case, it's a poloidal simulation, poloidal and toroidal in some other cases. And we can also change all these different types of things, which will be done by our mentees. So keep looking for that. But we do have the simulations, and they're really, really cool. So let me show you a movie. So again, these simulations, this is a simulation of the density. I think it's a velocity, but of a successful gamma ray burst. So the simulations also showed that we can get three potential things. So we can have that the jet breaks from the wind, we can have that it gets choked, or we could also have that the cocoon breaks out, but the jet does not. And yeah, so this is the velocity. So one takeaway that we can take from the simulations, other than the fact that, of course, since we have a torus, we will have what's called a magnetically arrested disk. This is going to form a jet. So one of the conclusions is that if there is bound mass from the dynamical ejecta, we could potentially quench the jet. So this ejecta is going to dominate the mass accretion, and because this ejecta is unmagnetized, it will suppress the jet formation. So again, if we have a powerful ejecta, we're done. The jet is going to be choked. And another conclusion is that the jet is mainly shaped by the disk winds and not the dynamical ejecta itself, which is also very interesting. We saw also the disk winds are the ones that I talked about before, the neutrino-driven wind and this accretion, this magnetized wind. And also the jet remains magnetized if it was already magnetized. So all of those are the conclusions from this really, really interesting paper that Or might talk about later. So if you're more interested, then you should go to his talk. And I want to say thank you very much. And if you have any questions, feel free to ask them.
Right. Thank you so much, Ariadna.
Thank you.
We have questions from the audience.
Yeah, so thank you. So in this, like the first thing that you were talking about, so as you said, it's all these 2D simulations and so on. So how well justified is the assumption that you can use 2D? So, you know, if I look at this 3D thing, yeah. I understand it's, you know, different scenarios slightly, but I know we also talked yesterday about tracking this full evolution from the beginning. Do you really expect that you can, you know, simulate things in 2 dimensions and you don't have some wobbling or whatever that influences?
Yeah, no, for sure. So that's a really big question, and that's usually the question that I'm asked. And yes, so with 2D, you can only say like a couple of things, right? You cannot do like very strong things, although I would argue that you can never do that with simulations, but fair enough. So the thing about 2D is that you always get a stable jet. So it's like really nice, it's pretty. But if you have 3D, you get all these instabilities. Like you can very clearly see from the movie, like you get all this weird instabilities. Well, no, not weird, but you get all these instabilities that only occur in 3D. Like this movie, of course, is very different in every sense than the one that I showed before. So yes, you do get instabilities that you should not get in 2D. So you cannot say a lot with the 2D simulations, but you can, of course, say some estimates and build some intuition. Like everything that I said again is built on intuition too. Like how much that if you interact more, then you will get more structure. Like all of those things you can for sure say with 2D too. And that opens the door for more and more simulations. Actually, so Gerardo's doing a 3D one too. Like the same author for this paper is also doing some 3D simulations, which are quite similar to this one, but for long gamma ray bursts. And also another thing that I'm going to maybe add that is not related exactly, but also we didn't use magnetic fields, but magnetic fields can be used to stabilize the jet. So if you have magnetic fields, you'll actually be able to stabilize the jet more. And we do expect the jet to be at least a little bit magnetized.
From their latest 3D simulation, it looked like the two beams of the jet are not symmetrical. It looks like
Yeah.
would that
Yeah, I
make
mean,
observationally different if you looked at the two different lobes? Would you infer different properties of the GRB?
that's a good question. Yeah, I agree that they're not quite symmetrical. And it's also because everything is all very self-consistently. So we do not put the jets. So the torus is going to wobble a little bit and you might get tilted disks and you're going to get very different jets. I don't know if we can say a lot about from observations because I don't think that we'll be able to differentiate them quite that easily. I don't know if the resolution is there to differentiate the very small differences yet. But very good question, a very good point. Like they are not symmetrical in this case. I agree.
I have a very naive question about this delay of the collapse of the hypermassive neutron star into a black hole. So what's causing this delay? Is it that in a merger you release a lot of entropy and basically you have some contribution of the normal pressure to the degeneracy? Or is it the rotation of the remnant, in which case you would need to understand how the angular momentum gets removed?
Yeah. So it's a lot due to the rotation. So this hot hypermassive neutron star is first differentially rotating, and that gives you a certain maximum mass. So I call this M max. That gives you a certain max. But when it goes into uniform rotation, you get a different threshold mass. So this M max is not the same as this threshold mass. So all of that are relativistic effects that highly depend on the equation of state. And you can say some things like where it should be around, but it's really hard to do so. And again, it's because a lot of the angular momentum transport is not very well understood. Also, like the magnetic fields are going to maybe alter some of these masses, but the magnetic fields are going to be very turbulent and very, obviously incredibly interesting, but also very turbulent.
So basically this delay time is determined by the efficiency of the angular momentum redistribution within the remnant. Is that?
I think so.
Okay.
And lots of other effects, like also. But yeah, it's mainly because the differentially rotating and uniform rotating neutron stars have two different threshold masses for collapse.
I have one question on your comment on dynamical ejecta in terms of choking the jet in your 3D simulation. Would it give you like how strongly does it depend on the angular distribution of the dynamical ejecta?
Yes, so that is
the equation of state and size of the neutron stars will either be predominantly in the equator, in which case it will probably not choke anything. But if it's the smaller stars, you get isotropic ejecta, and then those could choke. Right, so that might give you another angle on that problem.
Yeah. So in general, this paper was like the first in a series of papers. So this just came out. So one of the mentees should explore all this type of ejecta properties, like the distribution with the angle, the mass of the ejecta, also the radial distribution, because I think we use some -2 profiles. So all of these things will be explored in the future. They should affect it, and like as you mentioned, everything that happens in the equator doesn't matter that much. It's more like what happens in the polar region. So all of that is going to matter a lot, and we will explore that. But just like from this simulation, what we can get is that it's the bound matter that matters from the dynamical ejecta, and if the bound matter is less than 10⁻⁴ solar masses, you're good. If you have more, then you're more likely done for around that. So it will depend a lot on this dynamical ejecta, but more profiles to come. And in this case, this ejecta, I should say, is put by hand. So like we put a density profile and we put an angular profile and the mass. So we can explore, we can do a parameter search, which is in progress.
Do we have more questions? So let me check questions online. I didn't know. So with that, thank you again, Ariadna, for your nice talk. I'm sure if people have further questions,
And thank you very much for inviting me. I had a really fun time yesterday.
But thank you for taking the time for that.
No, of course.
All right.
Thank you.